lesson, we will be talking about acid and bases. In the last class, we talked about acid and bases, their basic property and their reactions. Today, we'll be discussing the last section, which is 7.2 and 7.3 of this chapter, which talks about oxides like basic, acidic, amphoteric, and how to prepare salts like soluble salts and insoluble salts. So before proceeding on to these two sections, I want to talk about acid salts. I want to give you a brief view of what acid salts are. So if you remember what monobasic, dibasic, and tribasic acids were, monobasic acids like HCl and nitric acid, they had only one H to contribute, so they were monobasic. So furic acid, on the other hand, is dibasic because it has H2SO4, which means it has 2 H, so it can donate 2 proton in aqueous solution. So the way you go about donating proton in aqueous solution can tell it whether an acid will give a salt or whether it will give an acid salt. A salt is formed when all the hydrogens of an acid are given out to form the salt. And an acid salt is, as you see, is something that has a proton in it, which means not all the protons from an acid has been given out. There are some H positive left in the compound form. So let me just give you an example of what I'm talking about. Let's suppose we take first off. Okay. So we take dibasic acid, which is H2SO4. Now H2SO4 is dibasic, it is reacting with NaOH. And according to balanced equation, let me just write down the balanced equation first. Na2SO4 plus H2O. So we have SO4, then we write over 2 over here. And there you have the balance. Do we have balanced equation? It's not balanced yet. 2H over here, 2H over here, that's 4, 4, 2, so 4, okay, that's lovely. This is the balance equation of a reaction between a strong acid and a strong base. Now, diving into how you get the desired products, let me just break down the equation into 2 steps. Now, why 2 steps? Because this sulfuric acid is a dibasic acid. So the first step of this reaction would be when you dissolve H2SO4 in NaOH, is that H2SO4 would give out, okay, my hand is sweating a lot, nothing new, H2SO4, okay, the writing needs to be fixed first and foremost. H2SO4 plus NaOH, they react to give. Now H2SO4, it has 2 H, so first off it will give only 1 H, and you take out 1 H from here, so 1 H and this OH from here would form H2O, and the leftover elements are, we have HSO4 and we have Na over here, so they react to form NaHSO4. So this I'm talking about over here is an acid salt. Now why is it an acid salt? Because it has an H in it. In the second step, this acid salt, NaOHSO4, would react with your, because it is an acid salt, so in nature it is acidic because it has a proton to donate. Therefore, being acidic in nature, it can react with the base to form salt and water. Now this acid salt is a monobasic acid by nature because it can give only 1 proton maximum in aqueous solution to form water. So this reacts with NaOH to form H2O. Now where did this H2O came from? We have OH from here and H from here, so they react to form H2O, and we are left with finally our Na2SO4. So there you go, final balanced equation. Now this is a 2-step mechanism of getting the purple equation I've written on top. So when you combine these 2 equations, so we have NaHSO4 over here as well, so this is cancelled out from reactant and product both sides. Similarly, we have, what do we have? Okay, that's all. That's it. So after cancelling out a product that a substance that is present in both reactant and product side, we are left with H2SO4. Over here, we are left with 2 NaOH on reactant side, and we are left with 2 H2O on product side and 1 salt. So there you go. This equation is just like the equation. Oops. Yeah, these two equations are exactly the same. This is how you get the final equation. Now this is for your dibasic acids. So now for instance, let's suppose we take phosphoric acid. Phosphoric acid is H3PO4. Now H3PO4, when I say H3PO4, you should know that it's a tribasic acid, which means that it has a ability to give 3 protons in aqueous solution, right? So now I'm gonna give you show you the entire equation of how to form all the acid salts. I'll just tell you that what kind of acid salt does phosphoric acid give, because it's a tribasic acid. So H3PO4, again we are acting with NaOH. So first off, it would give out H2O, and we are left with NaH2PO4, right? This is a dibasic acid salt. Now we react this dibasic acid salt with NaOH again. We have NaH2PO4 plus NaOH, and we get H2O, and we are left with Na2HPO4. Now this is a monobasic acid salt, because obviously it has only one H to give out in aqueous solution. Now this reacts with this acid salt reacts with NaOH again to form Na3PO4 and water. So there you go. That's how you get the equation for phosphoric acid and any alkali that you're reacting it with. The final equation for it would be H3PO4. Now, as you saw that I used NaOH 3 times, so 3 NaOH. We got 3 water molecules in total, and the final product is Na3PO4. There you go. That is the final equation for this reaction. So I hope this clears out what acid salt and what normal salts are. Okay, so we will be talking about preparation of salts. Now there are 2 types of salt. There are soluble salts and there are insoluble salts. Okay, we're gonna start off with insoluble salts. How to prepare insoluble salts. So our heading would be salt preparation, insoluble salt preparation or prep. Now there's only one particular way of preparing insoluble salt, and that is by reacting 2 soluble substances, and you are and there you go, you have your insoluble salt. So yes, we are going to take an example of an insoluble salt. Let's suppose we take silver. Fluoride is a very popular insoluble salt. Now you have a cation as silver and your anion is chlorine. So you need 2 soluble salts, and you will react them to form an insoluble salt and a soluble salt. So the overview of the general equation is, let me just write it down for you all. Okay. You have a soluble salt plus again a soluble salt. You react it together to form an insoluble salt and a soluble salt. Always remember, this is the only way of getting an insoluble salt, right? This is the only method that is included in the syllabus of preparing an insoluble salt. So coming back to AgCl, now Ag has silver as a cation, so now we need a salt that has silver as cation in it, and it should be soluble. Now silver chloride is insoluble, silver sulfate is again insoluble, silver nitrate however on the other hand all nitrates are soluble. So the best possible choice of picking out a soluble salt would be of nitrates. So AgNO3. There you go, we have one soluble salt, and the other would be, let's suppose, take NaCl, because NaCl again is a soluble salt. They react to form AgCl and they react to form Na sodium nitrate, which again, okay, my notebook is sagging a little bit, just give it a time. It's soluble, so let me just write aqueous. Again, this is aqueous, and this is soluble salt, insoluble salt as a precipitant. Now, okay, we have added silver nitrate, NaCl in a beaker, and they are reacting together and they are making AgCl and sodium nitrate as your two products. Now, how do you collect the desired salt, which is silver chloride in this case? I don't know why I'm saying always sodium chloride, but anyways. Now, there are two particular methods, there are two particular, let's say, ideas or keys you can use to identify if a reaction has gone to completion or if a reaction is no longer taking place. You get the point, right? So, of course, one reactant would be a limiting reactant, the other reactant would be in excess. As soon as the limiting reactant is finished being consumed, the reaction would stop. Now you have solid as your precipitate that you need to collect. So obviously you will be using filtration to collect the insoluble solid or the precipitate. So you filter the solution. Let's suppose we have this. Now this is your AgCl and the rest is the solution. So you take a filter funnel, put the filter paper on it, and then you pour the beaker. And there you go. And let's suppose we take this again, another beaker. So all the filtrate or the soluble part would come down to this beaker number 2, and you will be left with AgCl only on the filter paper, because obviously it's insoluble, it cannot pass with the filter paper. So you take it out, you wash it, you dry it, and then there you go, you have your AgCl as precipitate or as solid. That was all for insoluble salt preparation. It's a very simple topic, like a very simple section. You just take two soluble salts, react them together, you have a precipitate, you filter it, and there you go, you have your insoluble salt with you. Soluble salt. Coming on to soluble salt now. Soluble salt preparation. Now one method, I'm just going to write down all the methods first, and we'll be talking about one by one. So the first one is acid and metal. Okay, mind you, acid in all the 4 cases I will be listing down. Acid would be the limiting reactant, and the second reactant would be the one in excess, obviously. So okay. 2, we have acid plus metal oxide. Third would be acid plus metal hydroxide, or you can say alkali. In other words, it's easier to write alkali because it is a small word, and why write a bigger word. The last one is acid plus metal carbonate. So good job if you guessed it right. Now, all these metal oxide, alkali, and metal carbonate, all these are in excess, right? And okay, so before I move on to each one of them, I would like to tell you one important thing, that the metal used over here is obviously a solid. So is the metal oxide, because obviously metal oxide is very soluble, and the metal carbonate also is a solid. Alkali, on the other hand, is the only exceptional case. Alkali, this is the third one, is a reaction where both of them are soluble. The alkali is also in aqueous state. Right? So, because obviously alkali is an aqueous state, this is an exceptional case that I'll be talking about in the end. Now coming on to 1, 2, and 4. All these three methods, they follow the same procedure of collecting the salt. However, making the salt is a bit different in these three procedures, as you will see, because the reactants are different. Sorry, the products are different. Starting off with acid and metal. We know acid and metal make acid plus metal makes salt and hydrogen. Now, if you remember, I was mentioning a few while ago that there are two keys of identifying whether a reaction has gone to completion or not. One of them is by seeing the solid. Like for instance, we take a solid precipitate that is being formed in as a product. So there will come a time when the solid product won't be being formed, right? Because obviously the limiting reactant has been used completely. So that's when you know that okay, the reaction has gone to completion. The second one is production of gas. Now H2 or carbon dioxide, they produce bubbles or effervescence. The better word to use in your exams is effervescence for carbon dioxide and bubbles for hydrogen. So when you see that in a reaction, there are no more bubbles or there are no more effervescence being formed, that's when the reaction has been completed or the reactant has been used. So you can stop the reaction, you can collect the product. So in this case, you will be using your visual skills. You will be checking the bubble formation, and as soon as the bubble formation of H2 stops, that's when the reaction has been completed. Okay, so the reaction has gone to completion. It's been completed. Now you want to collect your salt. In this case, the salt is aqueous, so obviously filtration won't help in collecting the salt. If anything, filtration will only remove the excess metal. So now here comes the theory section of chemistry. You can be asked to tell how to prepare a soluble salt using acid or metal or any other reactant. Now this the answer that I'm going to be writing down is the one that we'll be using for method of preparation 1, 2, and 4, which uses a solid as one of the reactants. So preparation, the answer for preparation would be, this is the key points that you need to add or talk about in your answer to gain full marks. So procedure. Procedure includes, first and foremost, obviously, you take known volume of H2SO4, because H2SO4 is a limiting reactant, so you need to have a known volume of it. Known volume, I hope my writing is like unreadable, so I'm trying my best. Known volume of acid. Then you, in a beaker, obviously you take a known volume of acid in a beaker. Then you add your metal powder. It's in powder state to increase surface area and to increase the rate of reaction. Which you study later on that using powder state helps increasing surface area for reactants to come collide, and so the frequency of effective collision increases. Metal powder in excess. 2 beaker. Then you let the reaction go till no bubbles are formed. That's when the reaction has completed, no bubbles. Fourth step is filter. Now why are we filtering it? Because we do have a solid in our reaction in a beaker and we need to separate it first and foremost. So you filter to remove the excess metal. Filter to remove the excess metal, unreacted excess metal. The sixth step. Now here's where the fun part or the more important part begins. Now okay, you have the solid separated. Now how do you collect a soluble salt? The answer to it is through a method called crystallization. Now how do you do crystallization? Crystallization includes evaporation, and evaporation is one of its main highlight of the entire process. So you collect the filtrate, obviously first and foremost. Collect the filtrate. So the filtrate has your salt. Collect the filtrate, then you heat the filtrate to saturation point. Heating the filtrate or evaporate the filtrate to saturation point. Now you don't even know what saturation point is, but I'll tell you either way what saturation point is. Saturation point is, okay, so it's just a side knowledge. Let's suppose I have this crucible that I'm using. There is heat coming off, and this is my liquid. It's being evaporated to saturation point. Now how do I know that a saturation point has come? So you take a glass rod, okay, let's suppose this is my glass rod. You take a glass rod and you dip it inside the solution, just a little bit, right? Then you take it out, you take out the glass rod, and once the part that has been dipped is cooled, you see a few crystals. Okay, my drawing is horrible right now. You see a few crystals being formed on that end. That's when you know that saturation point has been reached and you need to stop the heating. Okay, so you heat the filtrate to saturation point. Then what you're going to do is you need to allow it to cool. Allow it to cool, so eventually the crystals will form in that crucible, and those crystals will obviously be of your salt. Now you collect those crystals. Crystals form. You wash them with cold water or any other organic solvent to dissolve the impurities. Cold water or organic solvent to remove impurity or dissolve the impurities and then remove them. Now you have your final clean crystal, and obviously because they are wet, so you need to dry them. You can use a sandpaper to dry the crystals, or you can use microwave to even dry the crystals. And there you go, you have your crystals. In this case, our crystals are, okay, we don't have an example, but let's suppose we used H2SO4 and we used zinc powder and they reacted to form zinc sulfate and H2. That this is our product we need, and we have finally collected the crystals of it. Okay, now this procedure, this entire procedure of 7-9 points would be the same for 1, for 2, and for last number 4. Now, why am I saying that? Is because in each of these three reactions, you will have an insoluble reactant in the state of solid that you need to remove once the reaction has been completed through filtration, and you will have a soluble product or a soluble solve that you need to collect through crystallization. And the way you do crystallization is obviously it's a universal method, and that is through evaporating it to saturation point, and so heating it to saturation point, then you allow it to cool, crystals form, then you wash them, then you dry them, right? So metal oxides, like let's suppose take copper oxide, now you're adding copper oxide with sulfuric acid, so you get copper sulfate. Copper sulfate is an insoluble, copper oxide and acid, copper, let's suppose copper sulfate, copper sulfate is a soluble salt. I'm sorry, I got confused. Copper sulfate is a soluble salt, so you can collect that through crystallization. Again, metal carbonate, let's suppose you take copper carbonate. Copper carbonate again reacts with sulfuric acid to form copper sulfate. Again, that's soluble, and you have carbon dioxide as the gas. So you see effervescence being formed once the reaction is taking place, and then there was no time when the effervescence will stop. And when the effervescence stops, that's when the reaction has been completed. So you can stop the heating, also, so you can start the preparation process to remove the excess unreacted reactant, which is in the case is metal carbonate. For metal oxide, so obviously it's an acid and an alkali. Now we don't have any gas. For an acid and alkali, we have acid and alkali react. Alkali react to form salt plus water. So in this case, there is no gas, but obviously you will be using acid would be your limiting reactant, and alkali, I'm so sorry, it's not alkali, it's metal oxide. Please don't write alkali. Metal oxide is your in excess. So when you have a limiting reactant, so after 5-10 minutes, all the acid would be neutralized. I mean, all the acid would have been used. So that's when you know, okay, the reaction has been completed. For this particular method, you don't have a gas to observe, and neither do you need one. It's just a matter of time, of estimating a time when all the reactant would have been used, right? So the answer key for this would be that let's suppose you take silver oxide, you add silver oxide to nitric acid, which is an acid, a strong acid, then they react, right, and they form silver nitrate. Silver nitrate is a soluble salt. So now metal oxides, by the way, this point is worth mentioning. Metal oxides, they require heat. In the reactions above, like acid and metal or acid and metal carbonate, heat wasn't required for the reaction to take place. But in the case of acid and metal oxide, you do need heat. So this is an exception again, that whenever you have there you go. Okay, this is an exception because this reaction requires heat to take place. So when you're reacting the two, okay, I think I should write down the procedure for this. For acid and metal oxide, it's gonna take 2 minutes. Okay, so acid and metal oxide. The first one is you take excess of acid, right? Sorry, you take known volume of acid. I'm sorry, known volume of acid. Then you take excess of metal oxide. Then the key word for this particular reaction, which is actually worth 1 mark, I believe, is you heat the solution to dissolve the reactant or for the reactant to react with each other. Heat to dissolve. Okay, so I'm going to tell you how you do this reaction, because obviously it's an exceptional case. Suppose we have this beaker. We have acid in it, right? Now we have a Bunsen burner as well, right? Because we need heat. So you are adding your metal oxide, which obviously is in solid powder state. So you're adding your metal oxide. Now, how do you know that your reaction is continuing or it has taken place? As you are adding the metal oxide in the beaker, all the metal oxide would be reacting with the acid to form soluble products, right? There will be no solid deposition at this particular state. But when all the acid has been used up, so obviously there's nothing the metal oxide can react with. At that particular point, solid deposition takes place. It starts to take place. If you observe solid particles being deposited at the base of the beaker. So once you observe the solid deposition, you can turn off the flame or stop the reaction. So what you can write is, you can add the metal oxide, until solid deposition, right? Now what you can do is remove excess solid by filtration, and then you can crystallize it, which is the exact method I mentioned over here as well, which is like basically 4 onwards, right? So this is some extra steps for acid and metal oxide reaction. Okay, now comes the fun part, which is we'll be starting off with our preparation of soluble salts. We talked about how to prepare soluble salts using 1, 2, and 4 method. We also talked about how to prepare insoluble salt, which is through precipitation, the only in one method. And now comes the exceptional case. Another exceptional case, which is using acid and milk. And the reason why I say it's an exceptional case because there is no solid involved in it, so there is no need of filtration, right? So for that, we need to have a complete new section to write on. Okay, there we go. You'll be starting off with acid. Which color should I use? Probably red. This looks very deadly, but I think I like it. It's too thin. Very nice. Acid plus alkali. Never mind the writing. Excuse my writing, please. Alkali is obviously soluble. Let's suppose you are taking the good old HCl and NaOH. Now these two obviously are aqueous solution. There is no solid involved. Again, they react to form NaCl and water. Now the reason why this particular section in this chapter is important is because it introduces a new part, which is titration. I don't know if you've heard titration word ever before, but today we'll be discussing what titration is in a bit of detail. Like the detail your syllabus wants me to go, that's it. Titration is a method, just like crystallization is. It's a method you use to determine unknown concentrations. Now, you are reacting NaCl and HCl, right? Now, you don't know what the exact concentration or what the exact volume of each of these two compounds should I be using so that I get the perfect amount of desired salt I want. For that purpose, that's where the titration boy comes in to help you determine the unknown concentration and the unknown volume. So what you do is, let's suppose you start off by taking a conical flask. You yellow, maybe mustard color. Good choice. You have a conical flask. Okay, there you go. Now in this conical flask, we will be adding HCl, 10 cm cube of. Then it's just a number, a random number. You can even take 20, you can even take 30, but it's better to take less volume of HCl for this particular case, because you'll know that eventually the burette has a limited volume of, like, it basically has a capacity, a maximum capacity to which you can add these unknown concentration or unknown volume solution in it. So it's better to use less volume, because obviously it increases accuracy as well. Okay, so you add 10 cm cube of HCl. It has 10 cm cube of. Now how did you add 10 cm cube of HCl? For accuracy and precision, you will be using a pipette. Pipette is again a device, not a device, but an instrument or an apparatus. Apparatus obviously is a better word to use. It's an apparatus. It is something like this. There is your pipette. It's pretty long. So yes, this is the pipette that we will be using to add 10 cm cube of HCl on the dot in this conical flask. Now above this conical flask, we have your burette. Burette is something like this. You have another line over here, then you have a thin section over here, and you have like this to close and open, and we have like the entire section is liquid. It has very like I think 0.01 graduations in it marked, right? So okay, now we have HCl in our conical flask. Now we need to have NaOH in our burette. So burette over here, burette में ही नहीं आता. Burette has NaOH, right? Because this is the setup of titration, of a classic titration. You have 10 cm of HCl in your conical flask. You added that using pipette. You have your burette which has NaOH, and now we need to add 1 drop of phenolphthalein indicator as well in the conical flask. Now I'm telling you why we need to have 1 drop of phenolphthalein indicator. Suppose this is like 1 drop. So this is your yes, phenolphthalein indicator. Now indicators are used to check when the endpoint has been reached. Now what is endpoint? Endpoint is when all the HCl in the conical flask has been used up. So obviously in chemistry we mostly rely on visuals, right? Like above we talked about how we can check the effervescence or bubbles. So right now we will be talking about color. Like we can see that at this point the color is changes. Okay, that is the endpoint. Now phenolphthalein in acid is colorless, but when phenolphthalein in alkali, however, on the other hand, is pink. So at this point, when there's only HCl in conical flask, when we haven't opened the tap, there is no NaOH falling from the pure into the conical flask. Phenolphthalein is the only thing, HCl is the only thing phenolphthalein is in, so phenolphthalein would give a color of colorless in HCl. Now as we open the tap, NaOH would start falling from the burette into beaker, into the conical flask, and obviously HCl and NaOH would react together, so they would so there won't be any excess NaOH at this particular point for phenolphthalein to give a pink color. But as soon as all the HCl has been used up, that's when the color would turn to pink and you need to stop the tap immediately. Again, I'm giving you a quick overview of what we are doing over here. We have a setup: 10 cm cube of HCl in your conical flask. You have NaOH in your burette. You have tap closed right now. You add 1 drop of phenolphthalein indicator into the conical flask. Now phenolphthalein and HCl is colorless, but when you open the tap, NaOH would start falling. NaOH and HCl react together, and as soon as all the HCl has been used up, there would be an excess of NaOH in the conical flask, and that's when the phenolphthalein indicator would turn pink and you need to stop the tap immediately. Right? This is done. Now we're writing the procedures of how will you be writing down your answer in the paper. Procedures. Let's use gray. First and foremost is fill burette. It's not E, it's U. Fill the burette with NaOH. Second is you use pipette to add 10 cm cube of HCl into the conical flask. Then you add 1 drop of phenolphthalein indicator. An indicator would obviously give a colorless solution and acid. After that, you open the tap and make sure you open the tap very slowly. Like NaOH should literally be dropping from the burette drop by drop. It shouldn't be running down. It should be falling drop by drop, right? So you open the tap and NaOH add NaOH from burette drop by drop. Drop by drop is an important word over here. Drop by drop. Okay. Sorry. Fifth point is, now as soon as the endpoint is reached, endpoint will be reached when the color of the indicator turns pink. You note down the volume. Now burette gives obviously volume measurement, so you note down the volume of NaOH used. Note volume of NaOH used. Seventh point is, now in this particular solution you can't be using the salt in this conical flask that you've made, because obviously this has indicator when it is impure. Now you know that what the volume of NaOH needs to be used for this particular volume of HCl, but you still don't know the concentration. You need to know two things when you're making the solution. One is the volume that I should be adding, and second is the concentration that that solution needs to have. So you use this formula, concentration into volume into moles, C1 V1 N1 C2 V2 N2, where concentrations, where C is for concentration, V is for volume, N is for moles, and 1 is, let's suppose 1 is for NaOH and 2 is for HCl. So you have V1, which is the volume of NaOH, which is found out. The number of moles NaOH and HCl react in 1:1 ratio. So N1 and N2 are 1. You have C2 and V2 because obviously you use known volume of HCl. Now you need to find out the C1, which is the concentration of NaOH. And once you have all the C1, V1 and C2, V2, so you will be adding those exact amount in another beaker, right? With no indicator this time, to get pure salts. So what you're gonna do is repeat titration. with no indicator. Ninth point is you have your salt, right? Because obviously all the acid and all the alkali have been used, so there's only salt left and water, obviously. So that's not, this particular point is where the crystallization process starts, which is you heat the solution until saturation point, then you allow it to cool down, then you filter the crystals, then you wash them with cold water to remove impurities, and then you have your NaCl as beautiful crystals with you. So that was all for preparation of salt, insoluble and soluble both. Okay, hydrated salts, hydrated substances, okay, this is very simple, to the point, nothing rocket science in it. Hydrated substance, as the word hydrated means that it has water in it. So like salts, normally a hydrated salt like copper sulfate is a hydrated salt. It has 5 molecules of water in it. Like it naturally has molecules of water in it, right? And we have anhydrous salt. Anhydrous salts don't have any water of crystallization or any, obviously they don't have any water in them. Water of crystallization refers to water salts like copper sulfate has. Like for instance, there's normally 5 moles of water, as the formula copper 5H2O tells you, and cobalt chloride also has 6 molecules of 6 moles of water in them. So the section is left. Oxide is a very small section. I could just teach you over here, but there's nothing much to it. Okay, so basic oxides. Oops, that's very big. Basic oxides, what oxide is? Oxide is basically any compound that has oxygen in it, right? Like a basic oxide is something that has a pH of above 7 and it would react with acid to form salt and water. Like metal oxides are basic oxides. We have, for instance, examples included in the syllabus are copper oxide or calcium oxide. These two have a pH above 7 and they react with acids to form salt and water. Basic oxides do not react with base. They do not. Okay, basic oxides can never react with base, and acidic oxides can never react with acid. An acid would obviously always react with a base. It can never react with another acid. That's the rule. That's a thumb rule. An acidic oxide, for instance, sulfur dioxide and carbon dioxide, they are acidic oxides have a pH of less than 7, obviously, and they react with your basic, like your bases, to form salt and water. Like for instance, let's suppose you are reacting carbon dioxide. Carbon dioxide is an acidic oxide. You're reacting carbon dioxide with a base, which is NaOH. It reacts. Now this is an acid, this is a base. An acid or base would obviously will always give you a salt and a water. So they react to form Na2CO3 and H2O. And you need to balance out the equation, so you have to over here and C1. Okay, that's about it. There you go. Amphoteric oxides, on the other hand, they are literally the king, the queen. They can react with both acid and base, right? And a few examples are, well, there are 3 known examples of amphoteric oxides: aluminum oxide, zinc oxide. Aluminum oxide is mentioned over here as well. Then we have zinc oxide, and another one that they didn't mention over here, but I'm just going to tell you anyways, but it's very basic, is lead oxide. Lead oxide is also another amphoteric oxide, and these can react with both acid and base. Furthermore, we have, okay, we've covered basic, we've covered acidic, we've covered amphoteric. Now we have neutral oxides. Neutral oxides are the opposites of amphoteric. They do not react with acid or base. So, well, they have mentioned neutral oxides over here, but I'm going to tell you anyways what neutral oxides are, because obviously you don't know what information is going to be used in what section of the syllabus. Neutral oxides examples are nitrogen monoxide, and we have carbon monoxide, and we have H2O. Okay, H2O, carbon monoxide, and NO. So NO, nitrogen monoxide, these three are example of neutral oxides, and they do not react with acid or base. That's all for this particular chapter. Thank you for watching, and I hope you enjoyed. If you have any queries, any questions, any suggestions, advices, or any critiques, you are always welcome to write in the comment section, and we will be looking, obviously we'll be coming back to those as well. So thank you.